Hi, this is Kevin Trainer, and welcome to my lecture on Chapter 8 of the third edition of Murach's MySQL book. And Chapter 8 is about how to work with data types. Um, we've been working as we've gone through the book, uh, starting with Chapter 3 and then up and through Chapter 7. We've been working with data types without really considering what all the possibilities are. You know, the databases that we've been using have been defined for us, the types already chosen, and we've worked a bit to see what the implications of those types are. And we'll be learning some more in Chapter 8, and we'll be learning even more when we learn how to define our own schema when we get up around Chapter 10. Okay? So, now we're going to learn some more. The objectives I'm going to leave for you to read on your own. The MySQL data type categories include character data, numeric data, or character types, numeric types, date and time types, large object types, spatial types, and JSON. JSON is certainly new to this book in terms of a supported type. Okay, exactly how new it is to MySQL, I'd have to look up. It's certainly supported in version 8, which is what we're currently using. So let's talk about the character types. We use a lot of character data. Uh, we have the char type. Now, some people call these things, the two types that we're going to talk about here on slide 4 are, I call them char and varchar. But I'm probably in the minority. Most people probably call them char and varchar. Of course, that implies that the word is character, which it's not. But you're going to adopt whatever pronunciation you prefer. So we've got two options. Option 1 is char is a fixed length. And so in this case, we've got the letter M to represent the length. Okay. And varchar is a variable length. And again, we're using the letter M to represent the length. But in this case, it's the maximum length. Okay. And if you look at bytes, okay, in terms of how much space does it take to store these types? Well, char, if we're using the newest of the UTF-8 encodings, that's part of MySQL. So a fixed length char a column will take 4 times the number of characters. And why is that? Well, that's because the new representation for characters, which is the true UTF-8 representation, uh, each character occupies from 1 to 4 bytes. And the way that it's handled for fixed length fields is we allocate 4 even if we use only 1. Okay? Whereas varchar, we're saying is length plus 1. And the documentation on this is a little sketchy, but um, uh, if in fact we are using characters that can be represented in UTF-8 with a single byte, then it only takes a single byte. Um, and so if in fact we're using, words that are in American English, for instance, and let's say that the length of the word that we have is 25 characters long, well, then it would take 26 to store it. If we were to use some other characters that can't be stored in 1 byte, maybe some bytes from European characters that have like accents and diacritics and that kind of stuff, well, they might take an individual character might take 2 or 3 bytes if it was that kind of character. The things that get stored in 4 bytes are kind of picture things. The best example of them is emojis. Okay, so the fact is that these varchars are very popular. I'm much more inclined to use them than the char equivalents. And I think as you look around the textbook and the examples in the sample databases, you'll see that a varchar is used much more often than char. Okay. Now, let's look at the examples here, because the first one, char2, which it looks like this, the column is the state column. One of the things I like about char2 for state is that states in the US have 2-character abbreviations, and that's a good documentation of that. Okay. You can see that the bytes that are used are 4 times 2 or 8. If it was a char 10 and we put just CA into it, we would use up 40 bytes because it would allocate enough space to hold the biggest characters. And again, the ones that take 4 bytes are things like emojis. And it would allow for 10 of those. If we have a varchar 10 and we put CA into it, well, it's going to be the length plus 1. It's going to be 3. If we have a varchar 20, we put California in it, we get 11. I think California is probably 10 characters long, so 10 plus 1. New York is probably 8 characters long, so 8 plus 1 is 9. Murach's MySQL is probably 14 characters long, so plus 1 is 15. Now, I just want to point out that although it doesn't seem to be that well documented, if we included characters in there that are not just plain old American English, US English, we might get, it might take up more space because of the possibility of multi-byte characters. Okay. All right. So those are the character types, and again, the popularity of varchars is very high these days. Now, what about the character types? Well, the original American and European English character set is called Latin 1. Latin 1 is very close to the character set that's available on PCs that are sold in the US and Europe. That's considered maybe too small of a character set these days, and we've gone to the Unicode standard. And one of the ways of encoding Unicode characters is called UTF-8. And now in the MySQL world, there are two implementations of the UTF-8 character set. Their original implementation, which is now dated and not recommended, uh, had each character could take up 1 to 3 bytes. And they did that to save some space, and then they did that because they didn't really see that people in the US in particular, but generally in the West, were going to need characters that took 4 bytes to encode. Well, it turns out that people who are doing chat applications, people who are doing blog applications, they're now getting emojis. And the emojis have Unicode encodings, okay, and they're done in 4 bytes. What most of them are, certainly. So there's been a change as we've moved to MySQL 8. There's been a change. The default implementation for UTF-8 has 1 to 4 characters. It's called UTF-8 MB4. And that's the character set that you're going to get on a new installation of MySQL. And that's the one that we've been getting in my last couple of teachings of this course. Okay? So that's the one that we want. Okay? And the reason it's better for us over UTF-8 MB3 in terms of our use here in the US would probably be emojis. Okay, but more clearly, UTF-8 MB4 is a complete Unicode encoding set, so we should be able to represent any character that's supported in Unicode, which is just about any character. Okay? So the takeaway here, we want to use UTF-8 MB4, and that should be the default that we're getting these days when we install MySQL. Integer types. Okay, so the basic integer type is called int. It takes up 4 bytes. Okay, and it holds whole numbers, no fractional parts. Okay, it's good for counts of things. Okay, and the basic int can hold a pretty big number, something like I don't know, 2 billion, something like that. It's pretty big. Okay, so there's generally speaking, when we're designing databases, if we have some count, we're going to use an int. Okay. Generally, for instance, if we're defining a table and it's going to have some primary key, and we have these keys where they're called surrogate primary keys, where they're just a single int value, and they make sure that all of the rows are unique from each other. And typically those are just plain old ints. And if you look at the databases in our course, the ones that come with the book, like APEXOM, and even the ones that we use for our assignments that came with the course, which is My Guitar Shop, just about every table has an int primary key. Okay. Now, why would you want to use other sizes? Well, you would want to use other sizes like big int if you have really big counts. Okay, so big int can hold really big integer numbers. Okay, and so you would want to use that when you exceeded the maximum value for ints. A typical alias for int is integer, at least in MySQL it is. Medium int, small int, and tiny int are smaller substitutes for int. Okay. Now, in terms of the practice that I recommend when you're defining a database, I would typically tell people to use int. If they had something that's big, to make it a big int, and not full with the medium int, the small int, and the tiny int. One exception is Boolean values. Okay, Boolean values are true or false. Okay. The implementation for Boolean values in MySQL is tinyInt. It's a one-digit value, okay? And the Boolean use, 0 is false and 1 is true. And there's even keywords you can use that alias the value. Instead of having to use the 0, you can use false. Instead of having to use the 1, you can use true. Okay, and that's something that we use in our course. So I would say if you've got a regular count, use int. If you have a big one that won't fit into int, or you're afraid won't in the long run, use a big int. And other than that, use a tiny int for Boolean. Okay, and Boolean is an alias for a tiny int. Okay. Now, the interesting thing about using tiny ints as a Boolean, whereas Boolean is an alias for tiny int. Tiny ints don't only have the values of 0 and 1; they can have the values of 0 through 9. So when you're assigning values, which you expect to be Boolean, and in our final project we have one. You have to remember that you're going to be assigning zeros and ones, and then when you print out those, it's polite, and then we have an instance of this in our final project as well. It's polite to check the values and to print trues and falses rather than zeros and 1, and you can do that with a function that we're going to be learning somewhere along the line here called if. Okay, so we're going to say if it's 0, it's going to be true, and if it's 0, it's going to be false, and if it's 1, it's going to be true. Okay, so those are the integer types. You can assign attributes to integer types. There's one for unsigned and there's one for zero fill. Okay, so if you look at the examples we have here on slide 7, the first two are assigned. Okay, the value of the first line is 99. The value of the second one is a negative 99. It stores the appropriate value, and when we display them, it displays the appropriate value. If we say that the int is unsigned, it will force it to be positive. Okay, that allows it to store a little bit higher numbers, which is maybe useful, maybe not. But as you can see, if we store on 99, it stores on 99, it displays 99. But if we try to store on negative, it won't do it. Okay, because it makes sure that you can't store a value with a negative sign in an unsigned field. Likewise, zero fill, which is for positive values, uh, zero fill is a feature that's used for typically if you want your integer to represent an account number or something like that, okay? Uh, you can get it to pad the left side with zeros, even though it would normally display it as just, as we saw up on lines 1 and 3, just 99. So if we say int zero fill, then we're going to get a lot of zeros to the left of the 99. If we say int 4 zero fill, it will contain it to 4 digits and pad the left with zeros. Okay, so the internal value is just 99, but when we do a select and we return a value, it's going to be padded with zeros. All right. Okay. Now, whereas the ints were good for counts of things because they were whole numbers, there are two ways for us to store number values that have a fractional portion. And the thing that's really, I think, great about SQL is it's got support for fixed point decimal numbers. Okay, so for instance, if we say decimal and we have the two values here, they're showing m comma d. Okay, what we do is we, I guess the m is supposed to refer to the maximum number of digits overall, and d is the decimal places, the places that are reserved to be to the right of the decimal point. The really good thing about decimals is that they add like dollars and cents. They're stored exactly as a decimal value. They add and subtract perfectly. If you have a column of numbers, you'll not get any rounding errors in the cents and things like that. So this is what we want to do for dollars and cents. If we've got dollars and cents, we might say it's a decimal 9 comma 2 or 7 comma 2 or 5 comma 2. So let's just go through the decimal examples while we can. So the first three examples here are 9 comma 2, so that means 9 digits of precision. Okay, so we call this first value the precision. We call the second value the scale. That's the digits to the right of the decimal point. Okay. So let's see, in the first one, we stored 1.2. It comes back as 1.20. It's got a fixed decimal digit scale of 2 decimal places. In the second one, we did 1, 2, 3, 4, 5, 6, 7.89, and that's exactly what we got. In the third one, we did a minus 1, 2, 3, 4, 5, 6, 7.89, and that's exactly what we got. Okay. In terms of the bytes that they use, there's a formula which says that you get the digits divided by 2 plus 1. Okay. No, I'm sorry. You get 1 plus the digits divided by 2. So 9 plus 1 is 10 divided by 2 is 5. Okay, sorry, touched the wrong thing there. Okay, so, and as you can see here, the fourth example is a decimal as well. 18 digits of precision, uh, 9 digits of scale, so 9 digits to the right of the decimal point. And as you can see, even though the value that we provided didn't have 9 decimal digits, it padded the decimal digits to the right. Okay, so let's see, let's figure this out. If we had 18 plus 1 is 19 divided by 2, the fact that they think that this can go into 8 digits, I think that's probably wrong. Okay, I think uh, it would be 10 bytes, but uh, that doesn't really matter. 8 bytes, 10 bytes, that's okay. Now, what are the other bit types that can have fractional parts to their values? Well, the other type that we have are these floating point types. And floating point types are good for, oh, they're good for math and engineering and science. Okay. But they're not good often for dollars and cents. Why aren't they good for dollars and cents? Well, they're the values are stored using scientific notation, and they're stored as binary values that are approximation of the decimal values that we assign to them. And we can get some problems if we add up enough of them, for instance, if we're using them for dollars and cents, for to be eventually off by a penny. Okay, so we don't want to use them for money in relational databases. We don't want to put money into decimals. But on the other hand, we can use them for all kinds of other values that could be, they're very good at representing very large or very small values because of the fact that they use this scientific notation. So what's the difference between a double and a float? Well, doubles have twice the precision of floats. Okay. Well, how does that come to affect you? Well, it comes to affect you in that with only half the digits being stored, you can have rounding that comes from the approximations. Okay. So what are the implications of that? Well, of course, we've already said if you've got dollars and cents to not use the floating point types, to use the decimal type. So, and then between doubles and floats, don't fool with floats. Okay, they're more prone to approximation errors, and unless you're going to be saving a lot of storage, like you're going to be, the difference between doubles and floats is 4 bytes. Well, that'll add up to a lot if you've got 50 million rows or 5 million rows, but it's not going to add up to a lot if you have 100 rows or 400 rows. So, yes to the double, a lot of suspicion on using a float. Okay. Terms to know about numeric data types. A real number, that's a number that has both a whole part and a fractional part. So both decimals and, decimals, floats, and doubles all can represent real numbers. Precision and scale. Precision is the number of digits Scale is the number of digits that are to be expressed to the right of the decimal point. An exact numeric type would be like an integer or a decimal. Okay, they're not being approximated with binary values, for instance. Well, that's not true. Well, there's no approximation. Okay, they're exact values, whereas floating points are approximate numeric types. Okay, and they're approximate because of a couple of reasons. One is that they're using binary values to represent the base 10 values that we're trying to assign to them and then to retrieve. And that becomes a problem when we add to it that we're approximating the number because we're not necessarily keeping all of the digits that we were given, especially with floats. We may just be approximating the number. Okay. And again, I typically say that you can use doubles to send a rocket ship to Mars. But I wouldn't use doubles to try to balance my textbook. And I wouldn't really use floats for anything unless you twisted my arm. Okay? Date and time. Okay. So we do have, we can have a column that's a date type. We can have a column that's a time type. We can have a column that's a date time type. We can have a timestamp, and we can have a year. Years these days are 4 digits long. We learned our lesson when we got to the year 2000. We've been doing 2-digit years since electronic computing had begun. In order to save some space, we decided when we got to the year 2000 that we had better be ready for the year 3000. And so, along with the other changes that we made, we decided that years would have 4 digits. So let's look at some of these. So what if we're storing things in a date? Okay. So here on the left side, we're storing a date character string in a date column, and it's interpreting as year, month, day. Okay. If we in the character string we haven't padded the values of months less than 10 with a 0, it's going to interpret them the right way anyway. So you can see here on line 3, we're doing pretty well because we say 18, 8, 15, and I guess it's able to figure out that 18 is the day, 8's the month, and 15 is the day. So, I'm sorry, 18 was the year, 8 was the month, 15 was the day. That doesn't seem to be a well-chosen example. If in fact we put all the digits in a string, it will allocate them out to the numbers. That's what we see with the next row. We don't have to put them into a string. We can use an integer that's 20180815, and we'll get the same value. We can have a string where we are separating the values by periods instead of hyphens. That's going to work. We can have one where we have a 2-digit year, a 1-digit month, a 2-digit day. That gets interpreted okay. 81518, however, is going to raise an error, so we're not going to get any value. And 2018-0231, which is not a proper day, we never have a 31st of February, well, that's going to raise an error as well, and we're not going to get value. Okay, so date values by themselves work pretty much the way you would expect. In fact, they're more versatile than in terms of what you can assign to them than you might think. I would say that the preferred encoding for dates these days, and for quite a while, has been this date format where we've got the 4-digit year, the 2-digit month, the 2-digit day. And when we put these with hyphens in between them, there is an ISO standard for this date format that's very popular. And this is probably the way that we want to represent dates in our code in terms of the way that we code the literals. So I would code the literal like we have on line 1 here, or I would code it, I would tend to code it that way. My next best alternative would be to show the same digits, not in a character string format. Okay? Okay. What about date times? Okay. Well, let's see. Here are literal values that are going to be stored to a time column. So it's going to take 732. I'm going to turn it into 0732. 1932 is going to turn into 1932. So it's going to work on a 24-hour clock. Okay, so that's 1932 is 7:32 p.m. We can put it into a string without the colons and get the same result, or we can just put it into an integer without any punctuations and get the same result. But if we try to assign a value that's not a normal value, if we try, for instance, to assign a value in which we have 61 minutes or even 60, it's not going to work. Okay. You can only represent up to 59 minutes before you add 1 and you go back to 0. Literal value, here's the value stored in a datetime or timestamp column. So we've got 2018-08-15, 1932-11. So it populates both the date and the time. What if you try to populate a date time or timestamp with just the date? Well, it'll give you the date and it will give you zeros for the time, which would be midnight exactly. Okay? I just want to point out here that the use of timestamp is attractive, but it's problematic. Okay? Do you want a date time or do you want a timestamp? Well, it turns out that timestamps have 2 features, one of which is kind of good, and the other is of which is both good and bad. So timestamps are take up less space in terms of the way that they're formatted. They take up fewer bytes than date times. So that's a potential positive. Unfortunately, the reason that they take up less space is that they're not able to represent values after 2038. Well, we're already in 2019. Okay, so uh, can you imagine writing code that would have a value or keeping data that we might keep for 19 years? Yeah, I can easily see it. For instance, is it possible that we might have a mortgage that would run for more than 19 years? Yeah. Is it possible for us to write a life insurance policy that's more than 19 years away? Yeah. Okay. So because of that, oh, so that's a downside to timestamp. The other nice thing about a timestamp is that when you insert a row for um, for a table that has a timestamp, it will automatically populate that field with the current date and time. Okay, but so that is sort of a nice convenience feature. Unfortunately, it's not going to be any good after 2038. So I'm recommending you stay away from the timestamp. Use the date time. It takes up a little more space, and you do have to populate it when you're doing an insert. You have to include the value, and so you would give it the value of the function now paren. But that's the way to do it. And timestamp is something that I'd recommend you stay away from. Okay, now we've got a couple of cool types called ENUM and SET. These are not part of the SQL standard. Okay, they're part of MySQL, and they seem cool, but I just want to warn you now that I'm going to talk you out of them. Okay, so how do they work? Well, here's how they work. So we have uh, we have an enum here. Okay, and let's see what we have here. We have we've defined a column. We said it's an enum of yes, no, and maybe. Okay, so those become the possible values. Okay, um, and let's see, if we try to assign it a yes, then we get the value yes. Try to assign no, we get the value no. We try to assign maybe, we get the value maybe, because those are all legal values. We try to assign the value possibly, we get the empty string. Okay, so it looks like we don't get an error, we just get an empty string. Okay, that's not very appealing. Okay, um, so in a lot of programming languages and other data technologies, this idea of having enumerated types where you don't say that you don't just say that you have a string that can hold any string, but only certain values are possible. Well, these are popular. They've been popular for 15 or 20 years. Um, so that's how you would do this kind of thing in MySQL. Again, I'm going to talk you out of this. Okay. What about the set? Well, the set is when you're not just taking on one value. Okay. What you want to say is that there's a set of values uh, that the column could take on. Okay, so the set, as we see here, includes these are pizza toppings, right? So it includes pepperoni, mushrooms, and olives. So if we try to assign it pepperoni, we get pepperoni. If we try to assign it mushrooms, we get mushrooms. If we try to assign it pepperoni and bacon, we get only a pepperoni because they can't take on the value bacon. Okay, so if we tried to assign the value bacon all by itself, we would have gotten empty string. If we try to assign the value olives and a pepperoni, we get them both, but we get them in the defined order. Okay? And this is, again, uh, in data-related technologies, there are a number of places where people have tried to implement set-like representations of things, and this is the MySQL version of this. And I guess it's okay. It's not very relational. Um, because, for instance, one of the things that we're going to learn when we get to designing databases is that well-designed relational databases follow the rules of well-formedness, um, and they don't have um, columns that hold uh, multiple values. They only have each column only holds a single value, and this actually breaks that rule. So it breaks one of the primarily one of the primary goodness constraints of good relational design. Okay, so you might say, well, Kevin, you're trying to talk us out of this. What do you have to offer that would serve the use cases that we just saw? And I would say, well, I've got relational technology. So I have another slide, which I created just this morning, actually, that shows examples of classic relational designs that we use as an alternative to the ENUM and the SET. Okay, and this is what I'm going to recommend. Okay, so I decided that I was going to represent a pizza order. Okay, but I was sort of inspired by the pizza toppings, I guess. So we have an order. We're assuming it's an order for a pizza. So it has an order ID. Let's make it a little bigger here so you can just see it a little bit bigger. Yeah, here we go. So we have an order ID. We have an order date and time. We have a customer name. And we have a size. Okay. And ordered pizza sizes: small, medium, large, extra large. Maybe there's another size. There's some kind of gigantic novelty size, right? Maybe there's a smaller than a small size. There's a personal. Okay. So what you do is you have a size table, a classic relational lookup table. It has a size ID that's an int. It has a size description that's a character field. And so we have a foreign key on each order that points to a row in the size table. Okay, so if we want to order a small, well, we point to the value small. If we want to order a large, we point to the value large. Now, why do we like this rather than enums? Well, number one, it's the relational way. Okay, relational databases have had lookup tables for 1 billion years. Okay, number two, the values are controlled by the user inserting rows into the size table. Okay, if we go back a slide here, all right, let me get back to that slide. Okay, there it is. If we go back 2 slides and we go to, where are we? We go we go to the enum. If we decide in the schema that the legal values are yes, no, maybe, and potentially the empty string, Okay, it looks like there are four potential values that you could find. Well, the problem is that if we decide that there's a yet another answer, we have to change the schema for the database. Do we really want to be doing that, or do we want the users to be able to think up a new size and just add a size to the size table? Well, I would rather the latter, and that's how we got the feature that we got. Okay, so let me very carefully take us back to my next slide. Where is it? Doesn't want to go. Here it is. Okay, so now we're back here. So user controlled, right? And the other thing that I'd like is we're doing a better job of controlling the values. As you saw with the enum, if we try to assign a value that's not part of the enum, we don't really flag it as not there. We just we store an empty string. Well, that doesn't really seem that good to me. Whereas in this kind of design, the size table defines all the legal values for size, and it controls the values. We can't create an order with the size that's not in the size table. Okay, that's why I like that. This is classic lookup table relational design. Well, what about the toppings? Okay, well, again, this is more classic relational design. We have the order. We have a topping lookup table. And again, we've got a topping ID and a topping description. And the values would be, well, the values that we saw in the pizza example. But, we could have pepperoni and sausage and anchovies and clams and pineapple if you can tolerate that, and spam if you can tolerate that, right? So we can have a whole bunch of things there. Again, this is a lookup table. It's a classic sort of a lookup table. We control the values, and it's user controlled. Any user who's able to add a topping to the topping table can decide that either we're going to continue to offer, typically, let's say that we decided that we wanted to order a spam topping. Well, the users could go to the right part of the system and add a row into the topping table. Okay, so does it work like the set does? Here, the order topping table is it's an associative table, a linking table, whatever you want to call it. Okay. In this case, it has these identifying relationships to the two tables it's linking. So this is the classic case of an associative table where its primary key is the combination of the two foreign keys. So it gets its identity from the order ID on the order table and the topping ID on the topping table. Now, this works exactly like the set does, because if in fact you try to order pepperoni twice, you can only have one a combination of an order and a topping. So there's no way to say that we want two toppings of pepperoni. There's no way to say that we want three toppings of sausage. Okay, it just won't work that way because of this being an identifying relationship. If we wanted to allow for double pepperoni, okay, all that we would have to do is we'd have to add a surrogate key to this order topping table, we call something like order topping ID. And then the order ID and the topping ID would no longer be the composite primary key for order topping. They just would be the foreign keys that point to the order and point to the topping. And then we could have either one topping of pepperoni or two or 25. Okay. Well, of course, that's not the way the set works. So the way the set works, you can only turn on pepperoni one time. So this is the design that does that. And again, this is classic relational design. Okay. We're controlling the values. Um, we're doing everything we're supposed to do. Again, I think this does a better job of controlling the values because in the set version, if we try to assign the wrong things, we're just going to get the empty string. Okay, so I would rather see you use classic relational features that are supported in all relational databases because these things are all supported in the SQL 92 standard. I'd rather see you use these than ENUM and SET. I don't think that you really do a lot. Now, why would people use ENUM and SET instead? It probably would save some space. Theoretically, it could save some processing time. But good relational databases are good at handling these small lookup tables. So I'm not exactly sure how much processing time you're going to save. Again, how many rows are in this size table? 5? 4? How many rows are in the topping table? 20? Okay, that's not a very big table, and certainly one the server is able to optimize access to. So I've hoped that I've shown you classic relational features that are, I think, more beneficial in the long run than getting seduced into using the MySQL features of ENUM and SET. All right, so we're staying on that. Okay, we got to get down to the next slide though. Can we? Yeah, go down to large object types. Let's do that. Okay, what are large object types? Well, uh, we use relational databases for so many things these days uh, that um, that we store things in relational databases that can be pretty darn big. Okay, so what things can get big? All right. Well, uh, we have these things called blobs. So what's a blob? Well, you know what blobs are. It's a blob of this or a blob of that. Now, actually, blob stands for binary large object. So what's a binary large object? Well, the classic ones that people are putting into relational databases, graphics files, a JPEG, a um, some photo format. Okay, sound, you know, MP3, uh, video, MP4. Okay, these are all binary files. Okay, we can store them in a column on a relational database. Okay, how big are they? Well, there's the original blob. Okay, uh, if you've got something a little bigger than will fit into a blob, then you can go to a medium blob. If you have something that's a little bigger still, you can go to a long blob. Okay, if you're trying to save space, it's binary, but it's not that large. So you have a bob, a binary object instead of a binary large object. Maybe you could do a tiny blob. I can't say that I've used anything but a blob. Okay. What about text? Well, uh, these are called clobs, character large objects. Okay. And so the type in MySQL is text, will get you a clob. And again, if you want a bigger one or a bigger one yet, you can go to medium or long. If you want a smaller one, you can go to tiny. Again, I'm sort of inclined to go to text. Okay, so those are all the column types that we're going to talk about. Now, when you have all these column types, okay, uh, you have to populate them. Okay, so you've got to get values into them. And then the other thing is that you need to retrieve values from them and either display them or use them in some kind of formula. So what we're going to go through now are a couple different ways to convert values in order to get some of the results that you might like to get depending upon the type. So how could you implicitly convert a number to a string? Okay. Well, you could, for instance, you could take you could say select invoice total, concat $ and invoice total. Okay, so you would get a $ in front of it. Okay, so if you look here, and again, I think I want to be a little bigger. If you look here, we've already got the decimal point, but we want to pick up the $. Okay. Next one, implicitly convert a string to a number. Okay, now how do you do this? Well, what you do is you use it in math. Okay, so what are we saying? We're going to have invoice number and then some large value divided by invoice number. Invoice number was the string, but it'll do the math anyway because implicitly we've said you have to turn invoice number into a number in order to do that math. You don't have to do it explicitly. Now, you could also add a 0. That I think would be a more useful way to convert the character to a number, right? Implicitly converted date to a number. Okay, so we have an invoice date, okay, and then we've got invoice date plus 1, which is going to add a day. Now, I just want to point out that you could add a 0 and not change the day. Okay, so that would be a better implicit way to convert a number. Convert a date to a number. All right, what else can we do? Well, let's see. Now, we just saw a slide full of implicit conversions. Can we convert things explicitly? And the answer is yes. And this might be something that we want to do in a formula where we would want to the problem with those implicit conversions is that they're not particularly good documentation. Whereas these explicit conversions, we're going to learn too, cast and convert, which do pretty much the same thing. They allow us to convert from type to type. So cast and convert have different syntaxes, okay? Cast is kind of almost a natural language kind of syntax. We say cast and we have a set of parens, but we say expression as type, okay? Whereas the convert looks more like a typical function. We say convert and uh, the input is the expression, and then uh, oh, I'm sorry. Um, the inputs are the expression and the cast type, and they're separated by commas. And of course, the output is the value that you've asked for. So what kind of types can we use in these kind of functions? Well, characters, dates, date times, times, signed integers, unsigned integers, decimals. Okay, so we're going to show you how to do a bunch of things, both as a cast and a convert. And in the coding assignment for this week, we asked you to do cast and convert alternatives so you can get comfortable with both. Now, would you use both? Well, I think you probably would adopt a style which would be to use either cast or convert, and you probably wouldn't go back and forth between them. Okay, uh, cast might be a little better. It's something that convert is, so maybe you would choose on that basis. But largely, it's a matter of style, and probably you're going to do adopt a style, and you're not going to mix them. But of course, we want to be sure that you know them both when you get to the end of the chapter. So here's what we're doing. We're selecting invoice ID, invoice date, invoice total, cast invoice data as char 10, as char date, cast invoice total as signed. Okay, so let's look at this again. Let's make this a little bigger so we can read it a little bigger. Okay, so invoice ID, invoice date comes out in the ISO format. Invoice total, the character date, not super different here. It's coming out in the same format that we're seeing for the invoice date. Okay, so we're not really changing that much here. And then cast invoice total as signed. Okay. And so invoice total, I think, if I'm remembering right, is a decimal with two decimal places. It's dollars and cents. So as we cast it as signed, we're going to be converting it to an integer. Okay, which means we're going to lose the decimal places, and we're going to get a round here. 138.75 cast as assigned gets rounded up to 39. 40.20 gets rounded down to 40. 3813.33 gets rounded down to 3813. Okay. So let's look at what happens when we go down here and we do a similar thing with convert. So it's the same thing except we're saying convert invoice date char 10, and we're saying convert invoice total signed, and we're really getting the same answers. Okay, so here it's clearly a matter of style. Okay. Formatting char functions. Okay, format is a way for us to format a number that's going to give us some value that we want. So in this case, we're formatting decimals. So again, we're formatting a decimal literal, but that's just for illustration purposes, to two decimal places. And as you can see, when we use format, we get commas and the number of decimal places that we ask for, and we also get rounding to get down to the decimal place. In the second one, we're getting the commas and the decimal point. We're getting padded zeros to get out the four decimal places. Okay, in the last one, we're saying that we want 0 decimal places. We're getting the commas, no decimal point, but we're getting rounding to get to that 1, 2, 3, 5. Okay. Char functions. Okay. There are some characters that we might want to print that don't appear on your average computer keyboard. Okay. Uh, Three that are popular to use are the tab, uh, which is probably represented by the tab key on your keyboard. Character 10, which is a line feed, and character 13, which is a carriage return. And whether you're getting carriage returns or line feeds is going to depend upon whether you have a Linux-based operating system like Mac OS or whether you've got, for instance, a PC. So it's kind of nice to be able to control spacing of things in the output by putting these special characters in. What's kind of interesting here is that we're saying we're going to concatenate the vendor name and then char 1310. So 1310 is a carriage return line feed combination. Vendor address 1, again, we do 1310. Vendor city, vendor state, vendor zip. Okay, and then we're getting these, it's doing this 1310 combination. Okay, to get the combination of a carriage return and a line feed. So that's how we get special characters into the output. Okay? And that is it. We're on 21 of 21. So, what to take away from the chapter? Well, what's kind of interesting is there are two sets of considerations here. One has to do with databases that are already defined. Okay. You can look at the definition now and know what values can fit into those kind of columns. The other thing is we've learned a little bit more about how to either format or convert the output of those columns to get the kind of values and appearances that we'd like to get. The other thing is we did have some discussion that it's going to serve us pretty well when we get into database design. So things like this. If we've got dollars and cents that we're putting into a table, then we probably want to use a decimal with 2 decimal places, right? If we've got a true or false, then we probably want to use a tiny int, or we could possibly use its alias, which is Boolean. Okay, if we want to keep some floating point number, we probably want to stay away from floats and prefer to go to doubles unless there's a really strong argument for wanting to use the float or the double having to do with we've got so many rows, we've got to worry about the space. Okay, and when it came to things like the ENUM and the SET, I've tried to talk you out of using enums and sets in favor of using classic relational design. So if you're following my lead, you won't be using the MySQL enums and sets. Okay, so that's it. I'm going to leave you to do your coding assignments and such. And I'm going to say bye until next time. Bye bye.